Okay, so continue from what we were discussing on last class, VS-EPR theory and shape of molecules. Now, and we have the summary chart of the VS-EPR theory that could help us determine what kind of geometry and shape a molecule or a polyatomic ion could take in a 3D space. Okay, and it's all listed here. And now, at the end of class the other day, we were discussing the tetrahedral geometry. Okay, and I found some pictures here, and here are all three of these are tetrahedral geometry. Okay, this one here is the CH4 that we were talking about. Carbon in the center, 4 hydrogens surrounding it, and giving you this very symmetrical geometry. And also because every ball here is a atom. This is the carbon, these 4 are the oxygen, the hydrogens. Okay, so the shape matches geometry because all of your electron clouds are bonds, all 4 of them. Okay, so geometry and shape match. Now, and if you look at ammonia, which when you draw Lewis structure, you would know that this is 3 bonds and 1 lone pair. And you can see 3 bond and 1 lone pair. You would have tetrahedral geometry, but it's trigonal pyramidal shape because now one of the 4 pairs of 4 electron clouds is actually a lone pair. Okay, 1 pair of electron, no atom on the other side. Okay, so when you're looking at the shape, you don't see the lone pair. Okay, you only see this part, and that's the trigonal pyramidal triangle in a pyramid shape. Okay, and actually, now if you go one step further, what if I have 2 bonds and 2 lone pair? Now, the very simple example would actually be if you draw the Lewis structure of water. Okay, you would have 2 bonds and 2 lone pair. How does the molecule look? Well, it's still geometry, tetrahedral geometry, because you do have 4 electron clouds. If you have 4 electron clouds, you have tetrahedral geometry. Those 4 electron clouds each need to have their own direction of extension, occupy part of the space, because they all have negative charges. They push each other away regardless if they're bonds or if they're lone pairs. Okay, but since only 2 of them are bonds, those are the 2 you could see. Okay, these lone pairs, they're not balls, they're electrons flying in the space. Okay, so the green things here you don't see, and what you see, this is why it's bend shape. Okay, and now if you have 5 electron clouds, okay, for example, if you have an easy example here would be phosphorus pentafluoride. Okay, and if you draw the Lewis structure, I think we've done this before. It would be phosphorus, fluorine, and then you would have 5 fluorine surrounding the phosphorus. Each fluorine has an octet. Okay, and in space, when every pair of electron gets the ability to extend out, then it would look like this. This is what we call the trigonal bipyramidal geometry. Okay, now, if you have 6 electron clouds, okay, like SF6, okay, why can you have 6 electron clouds? Remember the expanded octet that we talked about when we discussed Lewis structure. Okay, this could happen. Okay, they have, remember we said they have empty d orbitals they can use when they need to. That's this type. Okay, and when you have 6 electron clouds surrounding the central atom, those 6 electron clouds, okay, each would extend out and gave you all 90-degree angles, top, bottom, left, right, in, out. Okay, and this is what we call an octahedral geometry, as stated in here. Now, all right, we have discussed the different shapes with tetrahedral in detail. One last thing we want to mention here is that a tetrahedral structure, standard tetrahedral structure, the bond angle would be 109.5 degree. Okay, and when you turn it into trigonal bipyramidal, when you turn one of the bond into a lone pair, okay, like ammonia, okay. Now, supposedly this is still tetrahedral geometry. Supposedly the bond angle should still be 109.5, okay. But when you have lone pairs, now imagine lone pairs, because you don't have another nucleus on the other end of the lone pair to restrict it. So usually your lone pairs of electron, okay, they would extend out more. The space, those 2 electrons flying in is going to be bigger than the space your 2 bonding electrons in a bond would be flying in. Okay, and with bigger size, okay, comes bigger pushing force, bigger repulsion force, okay. So lone pairs repulse the bonding pairs harder than another bonding pair would do. And because this lone pair is pushing harder on these bonds, that makes the bond angle of ammonia shrinks a little bit from the standard 109.5, shrinks about 2.5 degree. So for ammonia, the bond angle between the 2 nitrogen-hydrogen bonds are actually only 107 degree. And if you're wondering, what about water molecule? What about when you have 2 lone pairs? And, well, 2 lone pairs push the bonding pairs harder than 1 lone pair. So you can imagine that your bond angle here is actually even smaller. Oops. Even smaller than the 107 of ammonia, and the actual measurement people have at this point is that this shrinks a little bit more at 104.5 degree for the bond angle between water molecules, and between the 2 oxygen-hydrogen bonds in water molecules. Okay, now, if you're wondering, well, what about trigonal bipyramidal or octahedral geometry? What happens when you have lone pairs in there? Well, now, for trigonal bipyramidal geometry, when you have all 5 bonds like PF5, okay, you would have trigonal bipyramidal geometry and trigonal bipyramidal shape. If you're only having 4 bonds and 1 lone pair in your 5 electron clouds, okay, then this here, one of the what we call equatorial positions will be turned into lone pair and invisible. And if this part is invisible, now what you see remember, you cannot see lone pairs. They're there occupying the space, but they're invisible. Okay, and when they're invisible, what you see, the molecule is like this, and that's why it's called a seesaw shape. Okay, if you can't see the seesaw shape like within what I circled here, well, try to turn your screen 90 degrees. Okay. Those are the two legs of the seesaw, and these are the two extended arm of the seesaw. All right, so one replaced. Now, what if I have two of them replaced? Well, if you replace another one with lone pair, another invisible arm of the trigonal bipyramidal equatorial position, and then you have this, and this is 90 degrees to that straight line, so that's why it's T-shaped. Okay, and linear would be easy to understand. What if I have three lone pairs? Well, you turn this into lone pair, okay, and what you got in the end is that's the only thing that you see. That, of course, is linear. Okay, and similarly, now once you draw your Lewis structure, if you find you have 6 electron clouds, okay, and again, electron clouds is every bond is counted as an electron cloud. Every lone pair is counted as an electron cloud. So altogether, if you have 6 electron clouds, you're going to have octahedral geometry. Okay, and if they're all bonds, it's octahedral shape. If there are 5 bonds and 1 lone pair, and you realize all 6 positions here are actually equivalent to each other if you just spin this around, spin the octahedral shape around. So if you take one of them and replace it with a lone pair, again, lone pair is invisible, so what you got left is actually this part visible, and that's why it's square pyramidal. This is a square, and this makes it a pyramid. Okay, and if you have another lone pair, that lone pair would occupy the opposite position of your first lone pair. Okay, and what you got left would be a square planar. Okay, so all these shapes are explained here. Now, for the trigonal planar earlier, if you have one of them replaced by a lone pair, that's why you got bent shape. Okay, so with different amount of geometry, there are only 5 of them. Okay, linear, trigonal planar, tetrahedral, trigonal bipyramidal, and octahedral. But for each individual geometry, depending on how many, okay, bonds and lone pairs that you have, your molecule could assume different shape. Now, a good way of practicing this is looking back on any Lewis structure that you have done. Okay. If you can draw the Lewis structure previously on your molecule, now you can look at them and try to determine the shape of those molecules. Okay. How does the central atom extend out? How does the electron clouds count on your central atom? And then from there, you can determine the geometry and the molecular shape. Yeah. All right, so one last thing of determining molecular shape we're going to talk about here is, let's go. For something like trigonal pyramidal, now, if I tell you, okay, well, the first lone pair goes in and replaces one of the equatorial position. The second lone pair goes in and replaces the second equatorial position. The third lone pair goes in and replaces the third lone pair, third equatorial position. And then a lot of times people wonder, why don't you replace these axial positions? Why are these two positions always stays with bonds? Okay, and this goes down to the repulsion force between lone pairs and bonding pairs. Look back. Trigonal bipyramidal is the only geometry that the only one of the 5 geometry, okay, that the positions on the geometry are not all equivalent. Linear, these 2 are both equivalent. Trigonal planar, these 3 are all equivalent. Tetrahedral, all 4 are equivalent. Octahedral, all 6 are equivalent. Only in trigonal bipyramidal, these 3 on the equatorial are equivalent, and these 2 on the linear, on the axial position, are actually equivalent to each other. And between these 2 types, they're not equivalent. Okay, so really only in this geometry we have that question, why do you go here, you don't go there? Because all the others, you replace a bond with a lone pair in the geometry, you can pick whichever, and you're going to get exact same result. Okay, so back to the previous pictures. You don't see an angle smaller than 90 degrees anywhere in these structures. Okay, here it's 180, here it's 120, here is 109.5, 107, 104.5. Here, you would have some 90 degrees. You would also have some 120 degrees, because trigonal bipyramidal is kind of like a linear and trigonal planar combination. Okay, and in octahedral is between every 2 electron clouds next to each other, it's always 90 degree. Okay, so you don't have anything smaller than 90 degree. And 90 degree repulsion is what we consider, because they're the closest, strongest repulsion. Picture. Okay, so this is the picture. So as long as you know how to draw Lewis structure correctly, and as long as you know, okay, with how to count the electron clouds within your Lewis structure, and then put it into each of these different geometry and molecular shape situations, and being able to figure out the shape, the geometry of a given molecule, a given polyatomic ion, then you should be good. All right? Yeah. And now, the next thing that we're going to talk about today, beyond the molecular shape, is that page. See, this is the ammonia structure. Okay, these 3 bonds, they're bond dipoles. They're all pointing downwards. Remember? Oh, they're all pointing upwards from hydrogen to nitrogen, going up. Okay, and when they're all going up, they're not going to be canceling each other on the going up direction. Okay, and ammonia would be a polar molecule. And then what about water? These 2 lone pairs, would these 2 bond dipoles cancel each other? No way. Okay, they're not 180 degree apart. So, yeah. All right. So we can actually look at the VSI EPR series summary here, and we can say, well, if it's MX2, 2 bonds, and let's make it clear, this need to be 2 equivalent bonds. Okay, if one end if you have carbon, something in the middle, one end you got chlorine, the other end you got fluorine, of course they won't cancel each other. Bond dipole would be different. But with the same bonds, linear would be nonpolar. Linear molecules would be nonpolar. Okay, trigonal planar molecules would be non-polar. Band molecules would definitely be polar. Tetrahedral molecules would be nonpolar. Okay, now trigonal bipyramidal would be polar. Bent would be polar. Okay, trigonal bipyramidal would be nonpolar because it's symmetrical. These two cancel each other. These three cancel each other because it's trigonal planar. Okay, seesaw, not polar. Okay, these two cancel each other, but these two won't. A T-shaped, definitely polar. Okay, a T-shape look like this. These two cancel each other. This one, there's nothing to cancel it. Okay, and then when you go back to linear, of course, linear is always nonpolar if you have the same bonds. Now, octahedral is definitely nonpolar. It's very symmetrical. Square pyramidal. Okay, remember the pyramid that we built here? Now, these four in the square cancel each other, but who's going to cancel this? You have a lone pair down now. You don't have a bond to cancel it. So, polar. Okay, and square planar, when you take two away, goes back to nonpolar. And this is all with same bonds in molecule. And if the bonds are different, then all bets are off. But if the bonds isn't different, then if the bonds are all identical, then this is your guideline on what molecules are polar, what molecules are nonpolar. Okay, it simply depends on the symmetry of the molecule and how does your bond dipoles cancel each other out. And this is the end of the lecture today, end of the discussion of polarity. Okay, and this is also the cutoff line for your third exam. Okay, your third exam is end at polarity of molecules. Next lecture, we're going to start to talk about hybridization and intermolecular force, and eventually ideal gas law. And those three things are going to be covered in only your final exam. What do you mean? Well, when we try to determine which position, and actually, no, do we choose the equatorial position, or why the molecule choose the equatorial position to replace with lone pairs when you have lone pairs. So this comes down to the repulsion force between lone pair and bonding pair. Okay, and the way that we are going to arrange a molecule, the way that we're going to put in a lone pair, we want to make sure we minimize repulsion within molecule. Okay, and how do we minimize? We're going to establish this, that for lone pair repulsion is going to be stronger than lone pair bonding pair repulsion, which is going to be stronger than bonding pair and bonding pair repulsion. Okay, and in all of these situations, we're only considering 90-degree repulsions because 90 degrees is the closest that your two pairs of electrons would ever get to. Okay, you don't see if you, and now when we because this is as close as two electron pairs ever get. Okay, now for your lone pair, now for the trigonal bipyramidal geometry. Now, your lone pair could go on equatorial position, the three 120 degree apart positions, or your lone pair could go on the axial position. Okay, but in each of those times, if you think about 90 degree lone pair repulsion, lone pair bonding pair repulsion, and bonding pair repulsion. Now, what you're going to find is, well, there's only one lone pair, so 0 of each. Okay, but for the lone pair bonding pair repulsion, if your lone pair is on the equatorial position, let's go back there. Let's draw this. If this is your center atom, and okay, so if you put the lone pair on the equatorial position, lone pair bonding pair 90 degree repulsion, where do you see it? Well, between this lone pair and this bonding pair. Okay, that's 90 degree. Between this lone pair and this bonding pair, that's 90 degree. And this lone pair with other two bonding pairs, it's beyond 90 degrees, so we don't worry about them. So lone pair bonding pair on equatorial is 2. Okay, what if this is on axial? You can see that if you have that lone pair, this is our lone pair. Well, on the axial position, this is 90 degree. This guy is also 90 degree to this dotted bond pair. This lone pair is also 90 degree to this triangle bonding pair. So you would have 3 of those. Okay, and you would have 4 bonding pair 90 degree. You would have 3 bonding pair 90 degree for equatorial and for axial position. Now, and this here is the reason, because the repulsion is same here, but it's different here, and we want minimize repulsion. 2 is less than 3. Okay, so that's why lone pair is on the equatorial position. Now, and again, this is an explanation if you have a question for why this is happening. Okay, now I'm not going after you to explain why in any of your exam questions. So for exam situations, we're going to discuss our earlier polarity of molecules. And now, what is polarity of molecules? To understand polarity of molecule, first we need to understand polar covalent bond. Okay. A polar covalent bond is a covalent bond that shared its electrons unequally. Okay. Now, we all know that covalent bond is sharing of electron pairs between two atoms. Okay, but sharing is different between different bonds. What do you mean? Well, think about your hydrogen sharing a pair of electrons and your hydrogen fluorine share a pair of electrons. Okay? Now, between the two hydrogen atoms, you have the two exact same nucleus attracting one pair of electrons. This is going to be equally shared. Okay, and when your electron pairs are equally shared, okay, we say that your bond or your molecule with that bond is a non-polar bond. Okay, non-polar molecule, or you can say this is also what we call the pure covalent bond. Okay, equally shared. Okay, but when hydrogen and fluorine are sharing electron pairs, you already know this. Fluorine is the element with the highest electronegativity. Okay, fluorine attracts shared electron much harder than hydrogen. Okay, so when these two are sharing, there would be an imbalance of the electron cloud between the two atoms. What do you mean? Well, they are sharing a pair of electrons, but that pair of electrons is going to be so much closer to the fluorine nucleus than it is to the hydrogen nucleus. Okay, now, so this is like you and your roommate ante up and bought this car. Okay, you and your friend ante up and bought this car. Equal sharing would be I'm driving it, okay, half of the time, and you're driving it half of the time. Okay, now that's what happened here. And unequal sharing is like we bought the car together, but you're driving it all the time, and I rarely see the car. Okay, and whenever you have this type of unequal sharing, we say, well, this bond here is a polar covalent bond. Okay, a polar covalent bond would create what do we call a bond dipole. Okay, what do you mean bond dipole? Okay, now the electrons are going to be so much on the fluorine that the fluorine end of the molecule, because this is the whole molecule, right? The fluorine end of the molecule, electrons are going to show up so much more, the shared pair of electrons is going to show up so much more that you have some partial negative charge. Not full negative, because that would make it an ion, okay? Until fluorine and take the electron and run. It's not a full negative charge, but the electron is going to be so much more accumulated on the fluorine end, you have a partial negative charge, and we use delta negative to represent it. And no, the hydrogen end is going to be so much electron deprived, okay, we say it has partial positive, and we use delta positive to represent. Okay, and when a bond has a partial positive and a partial negative end, we say you have a bond dipole. And so for a molecule, if you have a partial negative end and a partial positive end, we say you have a bond dipole. For a chemical bond, covalent bond, if you have a partial positive and partial negative end, we say you are a polar covalent bond with a bond dipole, and we show the bond dipole using an arrow with a tail to represent. The tail end looks like a positive sign, so it's pointing to the partial positive end, and the arrow is pointing to the partial negative end. Okay, so every polar bond has a bond dipole, which represent the imbalance of charge distribution. Okay, now imagine if each bond has this bond dipole. Okay, what if I have multiple bond dipoles within the same molecule? Okay, and the situation is going to be more complicated. Now, all right, for atoms that made up by diatomic molecules, the molecules that made up by two atoms, okay, whether they're polar molecule or non-polar molecule, is simple. HF is definitely a polar molecule because it has, so for diatomic molecules, okay, if you have a polar bond, you are polar molecule. And if you have pure covalent bond, you are non-polar molecule. Okay, that's easy. So HF, HCl, okay, are polar molecules. H2, N2, O2 are non-polar molecules. Okay, that's easy. But what about polarity of molecules with 3 or more atoms? Okay, and then your polarity of the molecule depends on the symmetry of the molecule. Okay, whether your molecule is symmetrical is essential to the polarity of the molecule. What do you mean? Well, do the bond dipoles cancel out? This is the question you need to answer. If your answer is yes, the bond dipoles cancel out, then okay, you have polar molecule. And if your answer is no, okay, is yes, they cancel out, then you have non-polar molecule. If your answer is no, they don't cancel out, then you have a polar molecule. All right, so let's see. first, let's see some examples. What about CO2? What kind of molecule it is? Well, if you draw the Lewis structure, you have, we've done this before. Okay, using the rules, we have two electron clouds. So, linear molecule. Okay, now, each of the carbon-oxygen bond are definitely polar bonds. Okay, as long as you have an electronegativity difference between the two atoms, you're going to have polar bonds. Okay, and because oxygen is having a higher electronegativity, if you look at your periodic table, than carbon, for both of the two bonds, you should be able to draw that bond dipole, because oxygen is the higher electronegativity, attracts electron harder. Oxygen is going to be the partial negative end, and carbon is going to be the partial positive end. Oxygen is the partial negative end, carbon is the partial positive end. But these two bond dipoles are 180-degree apart, completely opposite to each other, with actually the same strengths. Well, what do you think the result is going to be? It's like you're in the middle, okay? A pair of twins with the exact same strengths are dragging you on each of your left and right side. Are you going anywhere? No. And more than likely, the force of dragging from both sides completely cancel each other. So bond dipoles cancel, and you have carbon dioxide as a non-polar molecule. Okay, now, what if I have other shapes? The good thing about our molecular shape is that we said earlier, a lot of them are symmetrical, okay? And let's get back to some conclusion here is symmetrical structure with same bonds are going to result in non-polar molecule. What do you mean? Well, think about BF3. Okay, this is trigonal planar shape. Okay, this is a symmetrical structure with 3 axes. Okay, each boron-fluorine bond is actually a symmetrical axial to the triangle shape. Okay, and this is a non-polar molecule. Symmetrical structure, same bonds. Okay. Now, well, what if I take one of the bonds and replace it with a lone pair? Lone pair don't have bond dipoles no more. Okay. Now, if this is B, F, F, and then lone pair, then this is bent shape. Okay. Bent shape. Okay. Pretty obvious. These two are not going to cancel each other. They're identical, but they're not going to cancel each other because they're not 120 degree apart, 180 degree apart. That makes it a polar molecule. Okay. Now, what if you have CH4, the tetrahedral one? Again, that's tetrahedral. That's nonpolar. Okay, but the less symmetrical structure like ammonia, okay, if you don't remember,